looking at section 16.2, and that's what we're going to be focusing on today. And we're going to look at line integrals, and there is a number of different flavors to them. First one we're going to look at is a line integral that looks like this. You'll have some line or curve described parametrically as C, and if it's not described in a parametric form, you have to make it so. Some function of x, y, x, y, z, and ds, which is basically the differential in terms of the arc S. So in this case, it's xy squared ds. C is the right half of a circle orientated clockwise, and ds, if it's a two variable guy, x and y in this case, will be replaced by that guy. So essentially what you do with a line integral that involves x, y's, and z's is everything gets converted to t. And t is the parametricized version of the information. So if I take C and get it sorted out first. Now they're talking about the right half of a circle, and let me do a double check because there's a piece of information I need to know. And it's a circle, x squared plus y squared equals 9. Essentially, I needed to know the radius. Right, so this is C, and it's orientated counterclockwise, means that you're traveling along the curve in the opposite direction from a clock. That's fine. So basically, I want this fella here, this guy C. I need to find what he is equal to in terms of his parametric form. So I need to have an x, and I need to have a y, and this is something you just have to know. Circles can be parametricized. There's a word hard to say fast. Reasonably easily. Essentially, the information is very similar to polar. So wouldn't x equal 3 cos theta, 3 cos t, and y equals 3 sine t basically get you a circle? So I want you to think of the 3 as being the radius and the t as being theta. Isn't that basically r cos theta and r sine theta? So you want to do this guy. These are what the parametric version is. And I need to know, whoops, let's start again. What would t, the angle, be at the start, which is here, and then what would it finish up at here?
Negative pi over 2 to pi over 2.
Agreed. If you look back at some earlier questions, if I put a theta there, wouldn't that look exactly like polar form and cylindrical form, right? The t is like the theta, right? So that's our first job, to get this information. Now, there is a formula for doing this, fella, and the formula looks something like this. I'll get the next questions out of the way for a minute. And we're going to take this guy, the original question. Oops, X. And he's going to be from t equals negative pi upon 2 to t equals pi upon 2. The x is going to be replaced by 3 cosine t. The y is going to be replaced by 3 sine t, so y squared. And the ds is going to be replaced by this ugly mess. The derivative of this guy squared, if you differentiate this guy, you get negative 3 sine t squared. plus the derivative of y, which is this guy, which gets you 3 cosine t squared. So let's see what this line integral becomes. It actually becomes a Calc 2 integral. That's 3, that's another 9, so that's 27. It's going to get me a cos t. It's going to get me a sine squared t. That guy squared is 9 sine squared t. This guy squared is 9 cos squared t. Are we all okay so far? Do you know where all the pieces are coming from? This piece here is ds. This piece here is y squared. This piece here is x. So when you do a line integral of the form ds, everything gets converted into t's. And the way that we convert everything into t is to find out what the parametric equation of c is in terms of t. Okay, where do we go next? Well, let's have a look. Oh, let's skip some lines here. What's 9 sine squared plus 9 cos squared going to get me?
9.
And the square root of 9 is going to get me 3, isn't it? And that 3 is going to go with that 27, and that's where the 81 came from. Are you happy about where the 81 came from? I just don't want to have to write too many lines. Okay, you are looking at a Calc 2 question. So what technique will I use to integrate 81 cosine t sine squared t?
U substitution.
Agreed. So all we're left with now is picking the right one, right? Typically in these questions, isn't the u sub just sine t on its own or cosine t on its own? That's typically what you would choose, and this is one of the typical questions. So who is it?
Sine. Sine t.
Sine.
Correct. Wasn't a guess. I'm assuming that you picked it because it gets rid of the single cosine. Agreed? That would be reason. If you tried the other way, it doesn't come out very nice at all. So you differentiate with respect to t, and you get a cosine. You do the crossover, and then you isolate. So I am going to have an integral. I don't put the limits of integration in when you do a u sub. It's just not a good idea. So we have 81 cosine t u squared 1 over cosine t du. And we got one of the easy situations. Cosines cancel. And so I'm going to be integrating 81 u squareds, which is just a power rule. So that gets me 27 u cubed, which I'll then turn into sine t. So it's 27 sine cubed t. And then at this point, I'll put in the negative pi upon 2 and the positive pi upon 2. Okay, what's the sine of pi upon 2?
One.
Oh, yeah. You surprised me for a minute. Right, 27 times 1 cubed. Take away 27 times. What's the sine of negative pi upon 2?
-1.
Agreed. So basically that's negative 27, but when you subtract it, you add. So 27, add another 27. I believe the answer I got here is 54. So the line integral of this particular function traveling along this curve is 54 units. Are we comfortable about how you do the DS versions of line integrals? So at least how you do this one. Any questions before I move on to my next one?
What is this an example of? What problem number?
This one is an example of, hold that thought for a minute. It's an example of number 2. Question 2.
Thank you.
So, our next fella. Different kind of format. Do you see the line integrals don't have a ds anymore? They have a dx and they have a dy. So they look quite different, but they're still a version of what's called a line integral. And why is it? Are they all line integrals? Because you're integrating over a line or a curve C. Now, in this case, you've got an x plus 9y dx plus an x squared dy. And C is the lines joining 0, 0 to 9, 1, and then from 9, 1 to 10, 0. So I'm going to draw that, or at least a pseudo attempt at drawing it. So going to go from 0, 0 to 9, 1, which is here. And then from 9, 1 to 10, 0, which would probably be here. And this entire journey is what C looks like. Now, in this particular question, we need to actually split it into 2 pieces. And this line I'll call C1, and this line I'm going to call it C2. And so to get this integral, this line integral, I'm going to do C1 of all of that stuff plus C2 of all of that stuff. So all of that stuff means this. So I'm going to find this one and then that one. And the reason I needed to split it up is that this isn't like half a circle where you can have one single parameterization that, you know, does the whole thing. And these are 2 distinctly different straight lines in this case. And so I need to split them into 2 distinct questions. So let's get C1 sorted out. You want the line that starts at the origin and it goes to the point 9, 1, right? So basically this guy. Now the trick here is, how do you write it down in its parametric form? Right, we did the circle or the half circle one, right? That one we kind of borrowed information from polar. Here we're kind of starting from a kind of 0 point, right? So if you can imagine the line from here to here, what I'm going to do is I'm going to find the equation of that line first. You know, like y equals 2x plus 4, whatever. And then once I've got that, then I'll figure out how to do parametric of it. Okay. Would you agree that this straight line, right, the line that would go like this straight line has an equation that would be, let's see, its slope is a 9th. So it would be a very simple equation. Wouldn't it just be y equals 1/9 x? Are you okay with me doing that without doing too much math? Just rise over run. Now, how does that become parametric? When it's a straight line, make x equals t and make y equals 1/9 t, and now you've got the parametric form. So far, so good. Now, I need to know a start t and I need to know a finish t. Now, if you want the line to start at the origin and finish at the point 9, 1, want t start at 0 and finish at 9, and essentially the start and finish x value is the start and finish t value. Are we okay with that part? Any questions? We're good. Now, what on earth do we do about this dx and dy? I know what to do with the x. X is going to be t. I know what to do with the 9y. It's going to be a 9th t, right? I know what to do with x squared. It's going to be t squared. What I don't know yet is what to do about this dx, right? The differential dx and the differential dy. Because everybody, including the dx and dy, needs to be converted into things with t's. Well, I guess I've got plenty of room. I'll just do it. There is x. Won't dx by dt be 1? Yeah, like I was doing a user. And if I do my crossover, in this particular question, won't dx just turn into a dt? Now, what about the y then? Well, it's 1/9 t. So what will dy by dt look like? It will look like 1/9. And if you do the crossover, right, that's everybody in terms of t now. All these x's and y's are in terms of t. The dx and the dy are now in terms of dt. I know what the start and finish are going to be, t equals 0 to t equals 9. You put that package together and you're basically done. At least for the first part, right? This bit here. So for C1, the integral over C1 of x plus 9y dx plus x squared dy, that becomes the integral from 0 to 9 x plus 9y dx becomes dt plus x squared dy, which is that guy. So we get the integral from 0 to 9 of t plus another t, so that's 2t plus 1/9 t squared dt. Do you see our question has now just became a Calc 2? Are we comfortable about all the pieces, where they're all coming from? Right. But if we are, then the next line would be t squared 127 t cubed evaluated from 0 to 9. So that would be 81. Yikes, oh, 9, that gets a 3, 9 gets a 3, oh, 27. Take away a whole load of zeros. I believe the answer is 108. But that's only the answer for the first piece. Don't we still have to do C2? So I'll put a little bubble around that to remind myself. That's the line integral over C1. Now, what does C2 look like? It goes from 9/1 to 10/0. Imagine 9/1 is here and 10/0 is here. And so we need to go through pretty much the same process. It's a little bit harder to get the equation of this line because it's not passing through the origin. So if you look at this line, would you agree it's got a negative slope? Just using rise over run, what is the slope of C2?
Is it just -1?
Yeah, just -1. I need a point, so I'll choose that one. So that's going to be my x naught, y naught, and I'm going to use a guy called y minus y naught equals m x minus x naught. Do you remember the point slope equation from Math 94? So it's going to be y take away 1 is -1 x take away 9. And it looks like we've got an equation. Now, to make that parametric, x will equal t and y will equal -t plus 10. So it's quite easy, isn't it? If you can get the equation of a curve or a line, can't you just parametricize it by making x equal t and y equal the formula in terms of t? So if somebody said the curve was y equals x squared, from x equals -1 to 1, wouldn't you just make it x equal t, y equals t squared, and do the t from -1 to 1? So it's pretty easy to do, relatively straightforward shapes at least, and to make them parametric. Now, for this guy here, you can eventually prove that. And for this guy here, whoops, you can eventually prove that. Are you okay with me doing that in my head, or do you want to see where it comes from? That this leads to that, and this second line leads to this. Are you okay with that? Okay, so what do we have? We still have this fella, but we're now going to do it over C2. So it's going to be the integral over C2.
Would our evaluation of t still be the 0 to 9, or would it be?
Oh, you're right. I forgot to put that in. What are the range of t's to make this fella happen? Because it's not 0 to 1.
9 to 10?
Correct. And if you want to say, well, what do I use? Whatever the x starts at and whatever the x finishes at will be the start and finish of your t. So if your line starts at x equals 7 and finishes at x equals 27, your t will be from 7 to 27. Does that make sense? That your t range will be the same as the x range of the piece of the line you're talking about. So we've got this guy, dx, plus this guy, dy. And that's going to be from 9 to 10. This guy plus 9 times this guy. And instead of dx, we just have a straightforward dt. It's a 1-for-1 split. And then we're doing an x squared, which is this guy. And instead of a dy, you get a negative dt. So a bit crushed there. But you get the integral from 9 to 10. That's t. This is -9t plus 90. Take away a t squared. And that's -8t. Well, stick in 90 at the front. -8t, t squared. dt. Can I just dot that one? Isn't that just a power rule? Calc 2, plug in 10, plug in 9, and get whatever ugly answer you end up getting. Now, are we finished? Or is there one last step I need to do?
Do you have to add the results of both integrals together?
Yes. So the one I did get was 108. So just for argument's sake, can we pretend that's 42? I know it's not, but pretend it is. Then won't the answer be the first line integral, which we did do, which is 108, plus whatever the real answer to that one is. And now the final, no more work to do, is 150. Right, because you did the first bit and you got its answer, you did the second bit, but together you need to add them. Is it possible for line integrals to be negative numbers? Is it okay if that happens? What's your feeling?
Would it have something to do with the direction you went?
Certainly would. If you went the other way, you get the same answer but negative. So yeah, that is one way you could get negative, but you could just get negatives because more of the value along that line. I want you to imagine as you travel along that line, you're calculating combinations of x's and y's. In some situations, couldn't those x and y's be negative numbers? So if you think above being positive and below being negative, can you imagine my bad description last time of a fence where some of it's positive areas and some of it is negatives? So it is very possible to get negative line integrals. It's also possible to get zero. So there are no, oh, I got that answer, I must have done something wrong, right? You just have to trust the math and make sure that you did it correctly, and you should be fine. Are we good with that one? Do I move it? Last chance. We're good, I'm moving in. Lots of bits of paper today. I'll stick that there. Now, let's see who our next fella on my list is. Oh, it's a X, Y, and Z fella. So it's a straight line from here to here, and it's traveling through a dx component, a dy component, and a dz component. So this would be a line integral that's traveling through three-dimensional space. So I need to find the parametric equation of a line joining 2 points. And last week, was it? Yeah, no, 7 days ago, I guess it is last week. 7 days ago, my Calc 3 class were doing exactly this. So cobwebs out, how do you get the equation of a line in 3D joining 2 points? And we're talking about the parametric equation of a line. I'm going to tell you, but if you can remember, it would be so much better.
So will we take that second point minus the first one, and that's like, is that like
Yes.
sort of our slope equivalent?
It is. The jargon is, you're right, it is a slope equivalent, but we call it the direction vector. At least that's what I was calling it. If I call this guy P and Q, and the direction vector is the vector joining P to Q. And just like you said, second takeaway first, second takeaway first, second takeaway first. Are you happy about 5 takeaway 1, 1 takeaway 0, 4 takeaway 0? And that's how you find the vector joining P to Q. And then you just have to remember this equation. If you call this guy A, B, and C, and you pick whichever point you like, but I'm going to pick P, and that's going to be X naught, Y naught, Z naught, then the parametric equation is X naught plus AT, Y naught plus BT, and Z naught plus CT. So in this case, it's going to be 1 plus 4T, 0 plus T, and 0 plus 4T. And there is your parametric equation. Now, once you've got the parametric equation, it's probably a good idea, because I almost forgot last time. Are you all happy about where I'm getting the dx, the dy, and the dz from? Don't you basically do, differentiate and do a crossover, differentiate, crossover. But if you do enough linear ones, can't you just write down the answer? So far, so good. Now, I need a start and a finish t. For the line joining this fella to the line joining that guy, I need a start and I need a finish. And it's not really the same as what we did with the 2D straight line. In the 2D straight line, the x value at the start was your start t and the x value at the end was your end t. So if you think it's 1 to 5, and I can understand why you might think that, oh, t starts at 1, right, t finishes at 5, that's not going to generate this line. For 3D lines and beyond, that's not how you do the t values. It's actually very simple. What's the start and finish for that line from there to there?
0 to 1.
Exactly. Now, the good news is, if you use this technique, it's always going to be 0 to 1. Well, you can check it out.
So why is it 0 to 1 on this?
Right. If you plug in 0, right, won't you get 1, nothing, nothing, which is your start point?
Yeah.
If you plug in 1, won't you get 5, 1, 4, which is your finish point? And the reason,
so it's figuring
like-
it out with the respect to finding the equations for x, y, and z.
yeah,
And
the way
with
they,
respect to t.
yeah, the way the equation is generated, 1 unit of t will take you from the start to the finish, from P to Q. P is at the beginning, so t equals 0, and 1 unit worth of traveling, right, 1 t value if you like, and we'll get you to Q. So that's pretty much always going to be the case when it's a line joining 2 points in 3D space, that the t will be from 0 to 1. Right. Well, pretty much, aren't we good to go? Shouldn't I be able to turn the z's, x's, and y's into stuff? Shouldn't I be able to turn the dx, dy, and dz into t's? And shouldn't the c be 0 to 1? So it's going to be the integral from 0 to 1. Instead of z squared, it's going to be 4t squared. Instead of dx, it's going to be 4 dt. So I got that guy. Plus, instead of x squared, it's going to be 1 plus 4t's. That's what x is. Squared. And instead of dy, it's just going to be replaced by a simple dt. And then y squared is this fella. So it becomes t squared. And dz is 4 dt. So what do I get? Well, I get 16t squared times 4, so that's 64t squared. If you FOIL this out, you will get 1 plus 8t plus 16t squared. And if you distribute the 4 and that, you get 4t squared. And everybody shares a dt. Then I would do probably one more line. That guy and that guy, I believe, gets you 80. Then that one, that gets you 84. So 84t squared plus an 8t plus a 1 dt. And then dot, 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 dot.
I
Great,
think
it's
you
just-
swapped your y and z
Oh,
dt value.
let's check it out. So you think these are back to front, right? dy is dt.
Yep.
dz is 4 dt. It looks good. Let's
Oh.
check the y squared. Y squared is t squared. Yep. X squared is this guy squared. Yep. Z squared is 4t. It looks okay. Am I okay?
I'm looking at it wrong because I'm expecting the z to be z squared dz plus y squared
okay.
d.
You want the x, y's, and
Why?
z to match their dx, dy,
Yeah.
dz guys? Yeah. It would be nice, actually. It would be quite symmetric if it did that, but it didn't. Are we good with that question? Right. If I was trying to put in a theme right now, isn't the main theme that you need to find out what the equation of the curve C is in terms of t, right? You have to make it parametricize. Because once you got that sorted out, it's quite mechanical. The ds gets replaced by a big ugly square root guy, but if there isn't a ds, if it's a dx, a dy, or a dz, you just do this. Any questions about 5 before I move on to what will be our last one today?
Professor,
Yes.
is that a differential equation?
No.
It's not?
No. It's a line integral, essentially. A differential equation would be an equation, right? Let's repeat myself, but it's an equation that involves derivatives. So a differential equation might be something like this. And what you're trying to do is solve an equation. You are trying to not find dy by dx, although you typically might do that first. What you're doing really is you're just trying to find a function y where this is true. And differential equations are quite different. This is a line integral, right? It's an integral over a line, in this case c. So it's quite different. There is a little overlap in the sense that if you want to solve some differential equations, you may end up integrating things to make the solution happen. But that's only for some differential equations. In other differential equations, there are just different techniques. Okay, last guy for today. Actually, this fella is pretty much the what the rest of the questions are going to be about. I'm doing a quick scan. I'll take it back. No. No, there's a bit of A, a bit of B, a bit of C. Right. What we have here is a vector field. And you're going to be asked to do a line integral over a curve of a vector field dot dr. And they look like this, although you'll see that is bold and that is bold. And essentially the dr gets replaced by this fella, and the f gets replaced, all the x, y's and z, pardon me, that are in the f's get replaced by t. So though it looks different, it really isn't. It's really just more of the same. It's just maybe a notational issue. Oh, and it has a meaning. Yes, almost forgot. I may not actually get this guy done. So that's fine. I want you to imagine that f is your vector field, and your vector field looks like this. This is just some examples of little snapshots of the vector field, right? And C starts here, and it does its little journey, and it finishes down here. If you find the line integral of FDR, wasn't he an American president? FDR?
Indeed.
Oh. Now, see that funny dot? That funny dot is actually a dot product. If you want to find this line integral of f dot dr, right, FDR, what you are finding is the work done on traveling through this vector field. So, I don't know. Can you imagine this is the surface of a lake with currents in a river, and this red line is you paddling, and you started here and you paddled, and this is the route that you paddled along, right? This line integral would be the work done in getting from here to here. And sometimes you're fighting against the current, and sometimes the current is helping you along, right? So the work done it is possible to have work done 0 and negative. If the work done is positive, I think it means, from the concept of the way they think about work done, isn't that effort that energy that you had to put in to get the job done? If it was negative, wouldn't that be a situation where you actually got more energy out than you did putting in? Right. So a negative work is okay. Can you think of objects moving through magnetic fields? Or, oh God, I can't think of other examples, but anything with the word field in it. Can you imagine something moving through a something field? Then the work done there would probably be something you want to calculate, wouldn't it? So if you're trying to say, why should I do a line integral? The theory behind it is that it does allow you to calculate the work done in moving through some vector field, some field. And that's a very cool thing, you know. But this, I think, would be a good point for me to stop. And when you come tomorrow, we will finish off line integrals. Have we learned some cool stuff today?
Yep.
Yeah, taking me back to physics here.
Oh, do you know vector fields and work done? Is it that kind of physics?
Yeah, it relates to physics. And there's cool stuff like if your path is always perpendicular to the lines of the vector field, the field does no work on the particle or whatever you're looking at.
So that would be a 0 line integral?
Well, I don't know about the line integral, but the amount of work done is 0.
Well, since this line integral calculates the work done, I'm assuming it would be 0.
Yeah, most likely, I'd say.
Right.
I guess I want to calculate it and actually see that before I'm like, yeah.
Okay.
And there's cool stuff like you can have a gravitational field and do field lines with that too, so it's cool stuff.
Yeah. So some of you have actually used, when you've done it before, is it just the usual physics? Here's a magic formula, plug the numbers in.
Well, my professor kind of wanted us to know where these formulas came from, and we had to do a lot of derivations for them. But I would have to go over my notes to talk about that in any meaningful way.
Cool. So for those who are into that branch of math, here is a reason to find a line integral.